Hello. So this is a replacement lecture for the actual lecture that took place on September 2, 2021. So there was some problem with that recording and some mistake that I did, as a result of which I could not upload it to YouTube. So I'm recording this lecture again for the purpose of posterity, and I'm going to upload this to YouTube. Hopefully this one will be without any glitches. Okay, welcome to the fourth lecture of the one-shot information theory course. So today we will be studying Renyi divergences, continuing what we did last time, and then we'll move to something called smooth Renyi divergences. Okay. In the last lecture, we saw distinguishing measures between probability distributions P and Q on the same set X, and we studied the Renyi divergences of P with respect to Q. So let us recall, this is the L1 distance between probability distributions, okay? And this is the fidelity distinguishing measure, also known as the Bhattacharya measure, between two probability distributions. So the L1 distance is the metric, which means that if P is equal to Q, the L1 distance is 0. If P is not equal to Q, L1 distance is not equal to 0. It is symmetric and it satisfies the triangle equality. Now the fidelity is not a metric. In fact, if P is equal to Q, the fidelity is 1. If P is not equal to Q, the fidelity is strictly less than 1, as you can see from the Cauchy-Schwarz inequality. So it's sort of like an inverted metric in a certain sense, but not quite. I mean, 1 minus fidelity is not a metric, but we saw certain metrics which were defined in terms of fidelity. Okay. So one was the Hellinger distance, which is defined like this. Another was the purified distance, which is defined like this. And there was a relation that we proved between the L1 distance and the fidelity. So in short, the L1 distance is polynomially related to the fidelity, both lower and upper bound, as you can see. We also argued that the maximum L1 distance is 2, which happens if and only if the fidelity is 0, which happens if and only if the supports of P and Q are disjoint. Now recall that if the support of P is not contained in the support of Q, the relative entropy D is infinite. So in particular, if the supports are disjoint, then the relative entropy of P with respect to Q is infinite. After that, we moved on to a study of the alpha Renyi divergences. So this is the formula which defines it. So this formula holds for alpha in this range, strictly between 0 and 1, and strictly between 1 and infinity. In the last lecture, I had also used this formula for alpha equal to 0. So I tacitly assumed that 0 to the power 0 is equal to 0. But strictly speaking, this requires a justification why we are taking 0 to the power 0 equal to 0. So that justification comes from taking limits. So to make the understanding clearer, let us adopt this definition for alpha in this range. And for the special values of alpha, namely alpha equal to 0, 1, or infinity, we can define by taking limits. Or else we use this formula. If we do so, we saw that the Renyi divergence d alpha is continuous in its parameters alpha, as well as in the probability vectors P and Q. More importantly, we saw that d alpha is increasing in alpha in this entire range from 0 to infinity, both endpoints included. Okay. And this has some nice consequences already. So d alpha is greater than or equal to d0. And then we saw the expression for d0 last time, and we argued that d0 is always greater than or equal to 0 for probability vectors P and Q. In fact, if P is full support, d0 is equal to 0. Okay. And if P is not full support, then d0 can be strictly bigger than 0, maybe, maybe not. But in any case, it's always non-negative. And again, we have this property that the divergence of P with respect to itself is always 0. This holds true for all alpha. Okay. But as I just said, for d0, it can very well happen that P is not equal to Q, but d alpha is still 0. Okay, so there is no strict positivity out here. Okay, last time we also saw a relation between fidelity and the Shannon relative entropy. Okay, so we saw a direct proof of it, but from this property, namely that d alpha is an increasing function of alpha, we can get an alternate proof of it. So let us look at d half, alpha equal to half. You can check that d half is exactly negative twice the logarithm of the fidelity. Now the monotonicity says that d half is less than d1, and recall that d1 is nothing but the Shannon relative entropy. And the exponential relation between f and d, which seems to be implied by this statement, is in fact genuine. So in other words, there are probability distributions where the fidelity and the Shannon relative entropy are exponentially separated. You can cook up some examples of your own, or else we'll see such examples of probability distributions later on in the course. Okay, let's move on in our study of Renyi divergences. So an important property of Renyi divergences is data processing inequality. So recall that long ago when we studied Shannon relative entropy, we spent some time proving the data processing inequality for Shannon entropy. And in this course, I like to take data processing inequality in this formulation. So if I drop the register y, the distinguishability can only go down. In other words, the divergence goes down. So we saw a proof of this for Shannon relative entropy, which was d1, but this holds more generally for any alpha. Okay. And I had argued then that this formulation of data processing inequality also implies the data processing inequality for more familiar formulations like Markov chains or private kernel algorithms. Okay. And the same holds true even for DR. So really, the key is to show that dropping a register can only decrease the distinguishability, can only decrease the divergence. Okay, so to prove it, we'll use the convexity of this function x maps to x to the power alpha. So it is easy to check that this is convex for alpha in this case, strictly between 1 and infinity. And for alpha, strictly between 0 and 1, it is concave. Okay. So nevertheless, let's dive into the proof. So this is d alpha for pxy with respect to qxy. So this is the expression. Okay, so I'm just writing it in this funny form because I want to use convexity or concavity as the case may be. Okay. And then let's proceed further. So I can write the probability distribution qxy as this product qx, the marginal on x, times the conditional q of y given x. And similarly for p, I'll be writing. Now look at the inner term out here, the second summation over 1. So this has the form of an average of function values where the function is x to the power alpha, x goes to x to the power alpha. So if alpha is bigger than 1, it's convex. So I can apply Jensen or convexity. So average of function values is less than function value of the average. Okay. So okay, so this is the function value of the average. So I can pull that in out here. And for alpha less than 1, okay, I have concavity. So you may think the inequality goes in the other direction, but note that I have 1 by alpha minus 1, which is negative when alpha is less than 1. So that again reverses the inequality. So the long and short of it is that in both cases, alpha greater than 1 as well as alpha less than 1, I get the less than or equal to inequality out here. Sorry, this has to be greater than or equal to inequality. Okay, I get the greater than or equal to inequality out here. Do that. Sorry about that. In both cases, alpha less than 1 or alpha greater than 1, I have the greater than or equal to. Okay, so that's what I want. And now I can simplify it and get this expression and note that this is nothing but d alpha of px with respect to q. So for the special values of alpha equal to 0, 1, infinity, the same data processing inequality holds from continuity. And as I just said, this form of the data processing inequality implies data processing inequality in the private coin algorithm sense. It implies the non-negativity of the Renyi divergence, because I can take the private coin algorithm, which sends px to a singleton alphabet, and the probability distribution is 1 concentrated on the singleton set. Okay, and so no matter what px is, no matter what qx is, the private coin algorithm maps it to the same distribution. Okay, the trivial distribution of the singleton alphabet. Okay, and then d alpha of the trivial distribution with respect to itself is 0. So this proves the non-negativity. Then, as you saw, this proves the joint convexity, as well as analogous inequalities for the derived quantities like Renyi mutual information, Renyi condition information, etc. Same as. So really, this is the key inequality you should remember. Data processing inequality means that dropping a register cannot increase the distribution. So I forgot to mention this last time in the class, but let me mention it now. Data processing inequality also holds for the L1 distance and the fidelity measure. Okay. So for the L1 distance, this is the formulation. Okay. So the L1 distance between probability distributions Pxy and Qxy can only go down if I drop the register y. So again, dropping a register y cannot increase distinguishability. So for fidelity also that's the case, but remember, for fidelity, distinguishability means the measure decreases. So that's why it's less than. So it's easy to prove. For L1, you can prove the data processing inequality just by the triangle inequality of the L1 metric. For fidelity also, there's a very easy proof. Cauchy-Schwarz coming into play. Okay. So you can go home and try it. We will make use of the data processing inequality for the L1 distance in a few slides later. Okay, now let us define something new called smooth Renyi divergence. So one-shot information theory, as you see, deals with smooth entropic quantities, smooth divergences. So this smoothing is a very important operation. So why is it? Let me give you a high-level hand-wavy philosophical view. So divergences are an asymmetric measure of distinguishability between probability distributions. Informally, they capture the problem of asymmetric hypothesis testing. So here, I'm talking of divergence of P with respect to Q. So the interpretation is that Px is the so-called ideal distribution and Qx is the impostor distribution. Okay. So asymmetric here means that Px should work for our purposes with probability at least 1 minus epsilon. So it should work with probability something that is close to 1. But think of epsilon as a small constant. So it should work, let us say, with probability 0.9. 1 minus epsilon. Whereas the impostor distribution Qx should work with exponentially low probability. So the threshold for P and the threshold for Q are very different. The threshold for P is 1 minus epsilon, so just constant close to 1. Whereas the threshold for Q is not epsilon, it's not a small constant, it's something which is exponentially small. So that is why I'm using the adjective asymmetric for this purposes. And this is informally the paradigm of asymmetric hypothesis testing. The ideal distribution should work with probability 1 minus epsilon. The impostor distribution should work with exponentially low probability. So let's say I'm thinking of a machine learning algorithm, and the ideal distribution is the picture of my pet cat. Okay. And the impostor distribution can be picture of any other cat or a dog or a tiger, something like that. Okay. So I want to design my machine learning algorithm, which is nothing but say hypothesis testing algorithm. So my hypothesis testing algorithm should accept the picture of my cat with high probability, with probability 0.9, 1 minus epsilon. But more importantly, it should reject the imposter pictures of some other cat or a dog or a tiger, it should reject with very, very high probability, or in other words, the imposter distributions should pass off as my cat with exponential low probability. So this is a requirement. I don't want the imposter cats to enter my house, so I really want to guard against them. So they should pass the hypothesis test with exponential low probability. So all divergences are like that. The problem with divergences is that they're unstable. Whether it's a Shannon divergence or any Renyi alpha divergence, they're all unstable. So what this means is that a small change in the ideal distribution in L1 distance can cause a large change in the divergence. So in other words, let's say my pet cat grows old. So the ideal distribution Px gets perturbed to something P prime x, which is close to Px in the L1 distance. Let us say P prime x is epsilon close in L1 to P. Now, I don't want my machine learning algorithm to go for a toss. How can it go for a toss? So the machine learning algorithm will still accept my distribution P prime, the perturbed distribution with maybe probability 1 minus 2 epsilon. So P was being accepted with probability 1 minus epsilon. My cat has aged and now it looks like P prime. It will still accept P prime with probability 1 minus 2 epsilon. No problem about that. That's okay. But this should not throw, this should not throw the imposter pictures for a toss. So this should not result in a situation where now an imposter cat can pass off as my aged pet cat with significantly higher probability than me. So earlier it was very, very small, exponentially small. I don't want it to shoot up to, let's say, something like polynomially small, okay, or even a milder exponential. So this is my setting. Unfortunately, the divergences as I've defined are unstable. So these kinds of extreme jumps can happen. So I'm going to pause the recording now, and I invite you to come up with your own examples of probability distributions P and Q, okay, where a small perturbation in P to P prime can drastically change the divergence. So if you want, you can work with the relative entropy, okay, the divergence T1, the Shannon relative. Okay. Let me pause for 5 minutes. Okay, we are back now. Yeah, so here is a very simple example. Let us say I'm looking at probability distributions on a set of size 2. Now, let us say I take the probability distribution P, which is concentrated on the second element of the set. And Q is the same probability distribution concentrated on the second element of the set. I perturb P to P prime, okay, which looks like this. And you can easily see that the L1 distance between P and P prime is 2 epsilon. So it's a small perturbation. But now an extreme thing happens. The divergence of P with respect to Q is 0 because P is equal to Q, but the divergence of P prime with respect to Q is infinite, simply because the support of P prime is not contained in the support. So such things can happen. It can also go in the other direction, that the perturbation can suddenly drop the divergence. So you take the same example and run it backwards. Let's start from P prime and then go to P. That can happen. Okay. So this is something that I don't like and I want to avoid. So the idea being that if P prime is close to P in L1, then P prime should be almost as good as P in serving as the ideal distance. Okay. But unfortunately, as you've seen, the relative entropy of P prime with respect to Q can be much, much smaller than the relative entropy of P with respect to Q. And because my cat has aged, an imposter cat can pass off as my poor pet cat with much, much higher probability than before. I don't want that. So in order to avoid as well as take advantage of the above issue, yeah, to turn adversity into a benefit, what we need to do is we need to change the definition of divergences, and this leads us to define the smoothed versions of divergences. And the importance of smoothing will become clearer as the course proceeds. Okay. So here is how the smoothed quantities are defined. So let P and Q be probability distributions on the same set X. So fix an epsilon between 0 and 1. So this epsilon is called the smoothing parameter. Now the epsilon smooth alpha Renyi divergence is defined as follows. So it looks a little hairy, so we'll go through it slowly. So d epsilon alpha P with respect to Q. The epsilon smooth alpha Renyi divergence of P with respect to Q is defined as follows. For alpha in the range 1 to infinite, I do the following. Let us look at all possible perturbations of P to P prime, which are close enough in the epsilon ball. So that is this L1 condition. Now this P prime, I want to be less than or equal to P. So I could have dropped this condition, but it turns out in the minimization, the minimum is always obtained at vectors P prime less than or equal to P. So less than or equal to means P prime X is less than or equal to Px for every symbol X of my alpha. Or in other words, P dominates P prime pointwise. So this makes P prime into a positive vector, but it's not a probability distribution simply because summation P prime X in general will be strictly less than 1. So P prime is what is called a probability subdistribution. Doesn't matter, one can still define the Renyi divergence d alpha of P prime with respect to Q, same definition as before. Okay. So now what I do is that I try out all P primes less than or equal to P, with the caveat that P prime is in the epsilon wall around P, that is this. For such candidate P primes, I evaluate the divergence and I minimize over all candidate P primes. So this minimization gives me a real number, and that real number is the value of the smoothed alpha Renyi divergence. So this I have to do when alpha is between 1 and infinity. I have to minimize overall P prime in an epsilon. Now, if alpha is in the range from 0 to 1, okay, then I have to do the opposite. The same thing, start off with P, perturb P into subdistributions P prime, okay. So P prime is dominated by P pointwise. The caveat being that P prime is in the epsilon ball around P. And now I can evaluate d alpha of P prime with respect to Q, and I'm going to maximize over all P primes in the epsilon. So you may be wondering why this is defined this way. For alpha bigger than 1, I minimize in the epsilon ball. For alpha lesser than 1, I maximize in the epsilon ball. Why is this? So actually, this is a deep definition, and the choice of min and max comes with considerable hindsight. But let me see if I can give you some motivation right now already. So let us look at alpha equal to 0. So the extreme case out here, alpha equal to 0. So I'm talking of d0 epsilon, the smooth zero Renyi entropy. Now remember that if P is full support, then the Renyi entropy of P with respect to Q, the zero Renyi entropy, is always 0. So really one is not distinguishing between P and Q via this measure. Now, what I want to do is I want to perturb P to P prime. Okay, this will only be useful if after perturbing P to P prime, d0 of P prime with respect to Q becomes strictly positive. So in other words, at least for d0, the natural thing it seems to do is the maximization. Okay, and how will do the maximization? So I'll perturb P to P prime in such a way that the support of P prime is less than or equal to the support of P, strictly less than support of P in effect, so that the d0 can increase, right? So only if the support of P prime shrinks below the full support can I hope to get a non-zero value for d0 out. Okay. So at least for d0, it's clear that one should be maximizing here. Then there is this deep result, which we'll see more formally later on, that the Renyi entropies d alpha for alpha in this range look more like DC. And the Renyi entropies d alpha for alpha in this range look more like d infinity. Okay. So it makes sense with hindsight that for alpha in this range, in order to do smoothing, I have to do maximization epsilon bond. And for alpha in the other range, in order to do smoothing, I have to do minimization over epsilon bond. Okay. So for example, if you think of D1, okay. So D1 of P with respect to P is something, but I want to perturb P to P prime so as to make it less distinguishable. Remember, D1 or the Shannon relative entropy is unstable. Small perturbations can change things drastically. So here the aim is to make P prime, okay, less distinguishable from Q. So why do I want to do that? Maybe P was highly distinguishable from Q because of some pathological symbols X, where the probability of X under P is very different from the probability of X under P. But if I remove this pathological excess and the removal results only in a loss of epsilon in the probability mass of P, okay, maybe it's worth doing it. And for the rest of the symbols X, P prime X and QX are not so different. So in other words, the P prime and Q are pretty close. They're not so distinguishable. The distinguishability only came from a few pathological symbols. So this is usually a bad thing to do. And that's why I should remove those pathological guys and apply minimization in the epsilon. So that's, in a very vague way, is the motivation for these definitions. Okay. So let's take these definitions and go ahead. So now it's easy to see that d epsilon alpha is continuous in epsilon for fixed alpha. And it is non-decreasing in alpha for fixed epsilon, and it also satisfies the data crossing. So continuous in epsilon for fixed alpha, you can check that, because if you vary epsilon slowly, then the optimizing P prime also varies slowly. Okay, and remember, d alpha is continuous in its probability vectors, in this case P prime and Q. So you can put all these arguments together, make them rigorous, and conclude that d epsilon alpha is continuous in epsilon for fixed alpha. So we are not going to do the details in this course, but I just wanted to share some information, and we're going to assume this. Okay. Then d epsilon alpha is non-decreasing in alpha. In other words, it's increasing in alpha for fixed epsilon. So the way to see it, for example, let us say alpha is bigger than 1, and I take alpha less than beta. And the claim is d epsilon alpha is less than d epsilon beta. Why is that? Let us say I start off with d epsilon beta out here. So I have to minimize what P prime in the epsilon ball around P. Okay. So I find a minimizer. And now this d epsilon beta was really the d beta, the beta is Renyi divergence evaluated on P prime and Q. So I take that. And now I look at d alpha instead of d beta. Now, even for d alpha, this vector P prime continues to be the same epsilon ball around P. P prime continues to be dominated by P. So in other words, P prime is a feasible point in this minimization even for d epsilon alpha. Okay. So maybe the true minimum for d epsilon alpha occurs at a P double prime, something different. But that's fine, that can only drive it smaller. So in other words, d epsilon alpha is less than or equal to d epsilon beta. This is what we have. And finally, d epsilon alpha satisfies the data crossing inequality. So there is one point which you have to note out here. The rest of it is very simple. So we know that d alpha satisfies the data processing inequality. We saw that few slides earlier. Great. Now, let us say I fix an alpha. I am about to look at the private coin definition of data processing inequality. So I have distributions Px and Qx. There's a private coin algorithm which maps symbols in X to probability distributions over symbols in Y. So if I start off with the probability distribution Px and apply the private coin algorithm, I'll get the probability distribution Py out here. Then if I start off with the distribution Qx and apply the private coin algorithm, I'll get the distribution Qy out. Okay, fine. Now suppose I'm thinking of d epsilon alpha of Px with respect to Qx. Alpha bigger than 1. So to evaluate it, I have to find the minimizing P prime. Okay. So take this minimizing P prime on X. Suppose P prime lies in the epsilon ball around P. Okay, that is this condition. Now, if I apply the private coin algorithm, I know that it cannot increase L1. So in other words, so P prime Y lies in the epsilon ball around Py. Remember, Py comes from Px via the private coin algorithm, and similarly P prime Y comes from Py via the private coin algorithm. And since the private coin algorithm can only decrease L1 distance, P prime Y is a feasible probability vector for the smooth alpha Renyi divergence for Py and Qy. Okay. And then I have this, I have this minimization condition out here. So all the inequalities go in the correct direction, and I can infer the data processing inequality for d epsilon. So I did this proof in the air sort of for alpha larger than 1. You can do a similar proof for alpha less than 1. Maybe have to go in the other direction, but you can do that. Okay. So great. So all the d epsilon alpha satisfy data processing inequality. And smoothing removes the instability because I've already minimized an epsilon ball out here or maximized an epsilon ball. So there's no instability. So these are seemingly great quantities to work with. Of this, let's look at the two extreme quantities, d epsilon infinity and d epsilon 0. Now, if you remember d0, it was kind of stupid, right? If P is full support, d0 is always 0. So one would be led to believe that d epsilon 0 is also a stupid, useless quantity. But actually, it turns out that's not the case. So as will become clear later on, the most important quantities for one-shot information theory are d epsilon 0 and d epsilon infinity, the two endpoints of the Renyi parameter. So why is this? For those who have done a basic course in information theory already, you would have seen that proof arguments in information theory are of two types broadly. So there's a packing style argument and there's a covering style argument. So a canonical example of a packing problem is noisy channel coding. So we saw a proof of Shannon's noisy channel coding theorem at a very high level already. So the proof argument there is what is called a packing argument or a packing problem. Now the canonical covering problem is noiseless source coding. So we actually saw a proof of Shannon's noiseless source coding theorem in the asymptotic IID version. Okay. And it turns out that it can be viewed through the covering paradigm, and it's a canonical covering problem. One can look at generalizations of noiseless source coding, okay, and all of those generalizations are of the covering paradigm. Now, what it turns out, as we'll see soon, is that d0 epsilon controls the packing argument, and d infinity epsilon controls the covering argument. By controls, I mean Suppose you prove a packing lemma. If you look at the expressions that come inside the packing lemma, the entropic terms, you will see terms like d0 epsilon. You would say anything else. And if you look at a covering type argument, you look at the proofs there and you'll see that the parameters involve d infinity epsilon. Okay, that's what I mean by controls cover. Of course, there are proof arguments. There are proofs in information theory which use both packing and covering argument, in which case we will see both these entropic quantities coming out there in the one-shot ratio. Okay, that being said, so the take-home message is that these two are the most important quantities for one-shot information theory. So let us now look at d epsilon infinity. So one of the two important smooth Renyi divergences. So the d epsilon infinity is also known in the literature by d epsilon max. Okay, the epsilon smooth max Renyi divergence. Okay. There's nothing but definition. This. So here's the theorem. It turns out that the infinity epsilon has this formulation. This looks a bit hairy, so let's go through it slowly. So what is this? So to make sense of it, will become better as we look at the proof in this diagram. So we'll come to that, but let's make sense of the symbolically. So I have to define this notation. Remember, P and Q are probability distributions on the same sample space X. This quantity, curly braces, P minus 2 lambda Q, close curly brace with a subscript of plus. So this denotes the so-called positive set, or more precisely, the set of those symbols X, where Px minus 2 to the lambda Qx is greater than or equal to 0. So it's definitely not going to be the case that for all symbols X, Px is larger than 2 to the lambda times Qx. Okay. For some symbols, it's going to be larger. For some, it's going to be smaller. So for all the symbols where it's larger, you collect them up together, okay, and form this set. This is the definition of this. Okay. So now you understand the definition of this set: P minus 2 lambda Q, curly braces plus. Okay. And now we can understand this characterization. So d infinity epsilon of P with respect to Q is defined as follows: is the minimum over all thresholds lambda satisfying this property. Okay. So let us say fix a threshold lambda. This threshold defines me this set. Okay. This subset of the sample space. Now what do I want? I want to evaluate this linear function Px minus 2 to the lambda Qx, okay, over all x, over all little x belonging to this subset. So what do I want? After I evaluate this quantity over, I evaluate it only over all x's that lie in this subset. So after I evaluate this quantity, okay, in the so-called tail over the set, that should be less than or equal to epsilon. So that's what I'm talking about. So fix a threshold lambda. Automatically, this set is defined. Now, I'm going to evaluate this objective function over all x's, okay, over all symbols x that lie in this positive part. And now suppose I evaluate this quantity and it's less than or equal to epsilon. So the minimization over all thresholds lambda such that this constraint less than or equal to epsilon gives me my d epsilon max. Okay. So note that in D epsilon max there is P, Q, and epsilon. Okay, so let's prove this. So let's go back to definition. So D epsilon infinity of P with respect to Q. So we're in the first case out here, so there'll be minimization of P prime and epsilon ball. So what does the minimization do? I'm coming to that. Okay. So from the definitions, D epsilon infinity of P with respect to Q is the minimum over P prime less than or equal to P, such that P minus such that the L1 distance between P and P prime is less than epsilon. Let's say I found such a minimizing P prime. Then what I'm going to evaluate? Okay. So remember, I had this characterization of D infinity of P with respect to Q. So one characterization was the largest ratio of Px upon Qx. Okay. But there are alternate characterization which we saw, which sort of looks like this, is that you fix a threshold lambda, see it works for your purposes, that whether it satisfies this expression. If it does, put it in your bag and take the minimum over all such lambdas. Okay. So the idea being, why minimization? The idea being that if a certain lambda, if a certain threshold lambda gives me the value of the objective function less than epsilon, any lambda prime larger than lambda, okay, will also give me the value of the objective function less than epsilon. Why is that? If I increase lambda, the positive set here shrinks, it decreases. Okay. And if the positive set here shrinks, then I'm summing over a smaller number of x. Okay. I'm summing the same function over a smaller number of x, so it can only go down. So in particular, this alternate characterization of d epsilon infinity also suggests that the smoothing operation should really do the minimum of it, which is what we had. Okay. But now I hope the intuition becomes clear that we really have to do the minimum. Anyway, let's come back to the proof. So just from definition, d epsilon infinity is a minimization over all p prime lying in the epsilon ball around p of the largest ratio p prime x by qx. But that you can write in this fancy fashion, which will become useful notation later on. So what is the largest value of p prime x by qx? It is the minimum value of the threshold lambda such that p prime x by qx is less than or equal to 2 to the lambda for all x. And that's what is written out in terms of this vector inequality. Okay. How does one prove this? How does one prove the theorem? So we need to decide the set of x's where p prime is less than px. Okay. Now, once I have identified the set of such x's, I have identified okay. I have identified this set of x's with the largest value of p prime x by qx. So that is this expression out here. So to decide the set of x where p prime x is less than px, here's what one can do. You can check that it pays to arrange the x, the symbols x, in ascending order of px by qx. Once you've done that, you fix the lowest threshold lambda such that lowering px to 2 to the lambda qx for this tail, for the tail defined by x lies in this subset, this positive part. Okay. So what I want is that the process of lowering px to 2 to the lambda times qx for the tail defined by this expression eats up at most epsilon probability of. So let's see pictorially what this means. So the claim is that after I have done all these procedures, I get the optimal perturbation P prime of P. So this optimal perturbation P prime is close to P in the L1 distance, and moreover, P prime is dominated pointwise by P. So here is how one goes about identifying the P prime. So in this cartoon diagram, the x-axis denotes my symbols little x. The y-axis denotes the values of probabilities px, etc., qx, etc. Okay. And let us say my probability distribution look like this, and my the distribution, imposed distribution Q looks like this. So remember, summation x px equal to 1 and summation x qx equal to 1. So these vectors sum up to 1 out here. And now, if I draw them schematically, so I may get a picture like this. This curve is the probability graph of the probability function for the distribution P, and this curve in black is the one for the distribution Q. But remember, I want to identify the positive part of P minus 2 to the lambda Q. So to see it pictorially, let me move the probability distribution Q upwards by multiplying by 2 to the power lambda. Okay. So this Q moves up, and this curve is 2 to the power lambda times Q, which is just Q moved up. And now I look at the tail. So what is the tail? The tail is a set of those symbols x out here. So this is the tail. So this is a set of those symbols x where px is larger than 2 to the lambda times qx. In other words, x belongs to this tail set. Given like this. And now what is this expression? Px minus 2 to the lambda qx. So note that I'm going to evaluate this expression for a symbol x in the tail. So this is the tail. So the value of this quantity is the probability mass between these two curves. So the mass in gap should be less than or equal to epsilon. So this process, in fact, tells us what is the optimal perturbation P prime of P. So P prime is going to follow P up to this threshold indicated by the vertical line. And now, for symbols x to the right of this threshold, okay, so P prime follows 2 to the lambda times Q. So to the left of the threshold, okay, P prime follows Q. But to the right of the threshold, P prime follows 2 to the lambda times Q. So this is the curve marked in blue, like this. So now you can check that d epsilon max of P with respect to Q is continuous in its parameters epsilon PQ and satisfies the data processing inequality. So why is that the case? So let us understand continuity with respect to epsilon. Let us say I'm increasing epsilon slightly. So let's look at the original definition of d epsilon infinity. Let's say I'm increasing the epsilon slowly. Okay. Now, by this characterization, what happens? Okay. So I claim that if I increase epsilon, this so this distinguishability should go down, yeah, and so let's say I increase epsilon slowly. then the optimizing threshold here should also vary slowly. So why is that the case? Let us say increase from epsilon 1 to epsilon 2. So I'm going to allow more mass in this gap. Let us say epsilon 1 is less than epsilon 2. So I'm going from epsilon 1 to epsilon 2. So I'm willing to allow more mass out. So how do I allow more mass out here? Instead of raising the graph of Q upwards by a factor of 2 to the lambda, I'm going to raise it upwards by a smaller factor. Let's say theta. So instead of 2 to the lambda times Q, I'm going to consider 2 to the theta times Q. Theta is a little smaller. So this graph moves down. That means this threshold of this vertex given by the red blue line automatically goes a little back. Okay. So what does this mean? That I can increase epsilon. Okay, I can increase the mass in this gap. The way to do it is to lower this curve, which happened to be 2 to the lambda times Q, but I'm going to lower it to some lambda prime is less than lambda. Okay. So more mass can enter the gap. And now you can maybe feel why increasing epsilon will increase the lambda slowly. That is because a slight change in epsilon means a little bit or more or a little bit less mass has gone in, which means that this raised version of the curve Q need only be moved slightly. So this is sort of a hand-wavy description of why d epsilon max is continuous in epsilon. Then, of course, it's also continuous in the probability vectors P and Q, which you can easily check for yourself. Okay. And it satisfies the data processing inequality. That is because Dmax satisfies the data processing inequality. And I mean, that is property 1. And property 2 is that L1 distance also satisfies the data processing inequality. Okay. So this sort of gives a very high-level hand-wave proof that d epsilon max is continuous in the parameters epsilon, P, and Q. Now, note that d epsilon max can be negative too. Yeah, here in this picture, it looks quite positive, but in reality, it can be negative also. But these are pathological cases. So this usually happens when P and Q are very close in the L1 distance. So I would expect this D alpha or somebody to make use of this. So okay. So for the data processing inequality, I'll use the fact that any optimizer in the domain, which is in the epsilon ball, will get mapped by the private coin algorithm to something which also lies in the epsilon ball of the image. Okay. Okay. So in other words, to prove the data processing inequality of d epsilon max is easy. You just have to invoke the data processing inequality of the trace distance. Okay, d epsilon max can be negative. This usually happens when P is very close to Q and epsilon is comparatively large. So let us say P is very close to Q, so the two curves are very close to each other. Now, it turns out, so in fact, the curves are so close that the gap between P and Q, which is the entire tail, I mean, this is the meeting point and this entire tail. So the gap between P and Q, okay, is lesser than epsilon. So P and Q are that close. Now, if I'm going to look at epsilon smooth entropy for a larger epsilon prime, bigger than epsilon, okay, then what I can do is that instead of moving Q upwards, I can think of moving Q downwards. So if I move it downwards, what does it mean? It means that I'm multiplying by something which looks like 2 to the minus lambda times Q. So that this graph of Q moves downwards, and then more mass can appear in the region between P prime and Q. So moving the graph of Q downwards means that lambda is negative, which basically reminds us that d epsilon max can be negative 2. So here we call an alternate characterization d epsilon max. Let us look at the other end of the spectrum. So we are going to look at the smooth zero Renyi divergence. Okay, the smooth divergence for the smooth usage for the purpose of Renyi divergence. Okay, so d0 epsilon of P with respect to Q has this nice expression, very short, very sweet. Okay, so this is just everything opened out here. Okay, so I'm looking at P prime, point was dominated by P. P prime is close to P in epsilon, okay. And for such P primes, and for such P primes, hopefully the support is smaller, it is shrunk. So I can ask what is the probability of support of P prime under Q. Okay, and then take the negative logarithm, that is D0. But note that for the purpose of D0, only the support of P prime matters in evaluating the objective function to be minimized. Then really is the support that matters, because the support is the only thing that enters this. Now this support becomes a subset S of the theorem out here. PS is greater than 1 less. Okay, and all this is because an optimizing P prime should equal the original distribution P on this subset S. Okay, we had indicated what data processing should hold for d epsilon 0. So this again implies that d epsilon 0 is greater than or equal to 0. Okay, and d epsilon 0 of P with respect to Q is not continuous in epsilon. You can see like increasing epsilon means sudden leakage. Anyway, so one can use d0 epsilon and maybe connect it to ds. So first check easy that d0 epsilon is greater than or equal to 0 for all probability distributions Pn. Okay. Okay, so this is all good. I've put up P to P prime such that P prime is dominated by P. This is fine. And P prime is L1 close to P. P prime is epsilon close in L1 to P. And that's also a requirement. This is fine. Okay. But what is not fine, which you should check and convince yourself that d0 epsilon of P with respect to Q is not continuous in epsilon. So why is this? Let us come to this characterization of d0 epsilon. Let us say I start increasing epsilon slowly. Okay. Increasing epsilon translates to this subset S can only increase its cardinality. Okay. But increasing the cardinality means that one more element has entered the subset S. Okay. But what is going to happen? I'm increasing epsilon slowly, so that's a slow, smooth increase. But at a certain point, I realize that, oh my God, epsilon is so large that I can now further reduce the support of P prime. Okay. So I can shrink the support of P to get a new support. So shrinking the support only lowers this quantity, the probability of the set under the distribution Q. So note that for D0, only the support of P prime matters in evaluating the objective function to be minimized. And this support becomes a subset S of the theorem, and so on. Okay. So we'll stop here today. Okay. And I will see you on Tuesday.